we want to take a derivative and integral and that kind of stuff, right? So let's remember what this equation was. Equation of cycloid was x is equal to r, and you have t minus sine t, and since we are all working on how to derive epitrochoid, these are very easy and nice, right? You can derive it if you want to, and this is 1 minus cosine ta. Now I want to find out what dy over dx is. Okay, the theory. I'm not sure if you remember this theory, but let's do this. I'm gonna leave some space here. Dy over dx. Do you believe that this is dy over dt over dx over dt? I mean, that's what I taught you and you kind of accepted it. Of course, that should be the ratio, but why? Can you prove it? How do you prove such a thing, right? Let's prove it. Proof is a strong word. Let's not use that term, but here's a very strong, convincing argument, okay? Now, that's t. Let's just think about it. Suppose we can eliminate. Suppose we find the inverse function, so it's like x is equal to some function of, and then I'm using x as a function notation as well, right? Function of t. And then could we say then find the inverse function? Like that? You know what I'm saying? So we can find the inverse functions. I mean, this is very difficult to do, but theoretically we should be able to find the inverse, and we shove it into, and then substitute into y is equal to this thingy. That to that t, right there is where you want to substitute it. Then what you get is this. So we have a y as a function of t, but then that's a function of x. You understand this notation? So really, y is a function of x, but y is a function of t and t is a function of x. Oh, and then remember Turducken? Chain rule applies, right? So if you take a derivative with respect to x, that is same as taking a derivative with respect to t and take a derivative with respect t as with respect to x. That's chain rule now, isn't it? Now let's just think about this. Well, dy over dx on the left-hand side, and on the right-hand side is, of course, is this. You find the reciprocal and then put it right there, hey? How about that, hey? Okay, so here is semi-proof of what that thing is. Now let's come back to this thingy then. So if I make a copy of this, actually, maybe I should reverse the. I'll make a copy of this. I'll make a copy of all of it, and then redo it. I'm gonna paste it right there. Okay, so let's do this again. I copy the dates as well. Okay, let's do this over. So if we have such a thing, now we want to be able to take a derivative. Okay, so we need this. We need dx dt, which will be r and 1 minus cosine of t, and then we need dy dt, and which will be r sine t, eh? You agree? Okay. Then, of course, dy over dx is dy over dt over dx over dt, eh? Which is, if you simplify sine t over 1 minus cosine t. How about that? Okay, now I want to find out where is it vertical. Oh, by the way, is this thing, is it velocity? No, 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 no. This ui over dx is never, it's not velocity, right? What is our velocity? See, remember velocity, this r vector function is what this thing is. T minus sine t, and then r 1 minus. This is now, remember these are vector functions, and our velocity will look like this. The derivatives of these things. This is what our velocity looks like. That dy over dx, like I have never last year used that dy over dx as a velocity. You have to have a t in the denominator. You know what I'm saying? Meters per second. So that's not velocity. It just tells you the increasing, decreasing thingy, right? So now our question is, where is that thing? I'm going to move this thing down. Where is that thing vertical and where is that thing horizontal? Okay, now if you just look at it, it's got to be vertical, horizontal, vertical, right? Horizontal, vertical. So this is 2 pi, right? Do you see this is pi? Do you see that one revolution, one cycle is 2 pi, and then this is 3 pi, and this is 4 pi now, isn't it? Okay, so let's see if we can get that thing done. So we want to do vertical and horizontal, okay? Which one first? That's the horizontal. Horizontal meaning your numerator is equal to 0, or you can think like this. This is equal to 0, right? Your y movement is equal to 0. Your velocity y component is equal to 0. You know what I'm saying? So you take this to 0, you set the numerator or the whole thing to be 0, and that means sine t is equal to 0, right? That means t is equal to n pi, k pi, right? Okay, so we got this answer. And then vertical. I'm going to push this thing way, way, way down. It's quite annoying. Okay, then vertical is when the denominator is equal to 0, right? Also known as where your velocity x component is equal to 0, so there's only vertical motion. You know what I'm saying? We are thinking of this as a physics, like the particle motion always. That's what this class is for. And then you set 1 minus cosine t to be 0 then, eh? Right, that means t is equal to 2n pi a, because cosine t has to be 1. Do you see the conflict between the two? What is the conflict? Well, what happens when, see, this thing includes 2 pi. Right, it tells you that thing is horizontal here as well. So we have a conflicting answer. How do we resolve this two? Is it vertical or is it horizontal? Let's say 2 pi. Yes. That's the question. How do we figure this thing out? Because we have a conflicting answer. Huh? I know, but say this is too complicated, we cannot feel it, or we just need to analyze it. Then how do we? L'Hopital, we let L'Hopital settle this. So we let t approach pi over 2. Let's just do it from the right-hand side. I think the other side works out the same way. Of this thing, dy over dx. because the numerator will approach 0 as we verified it, and the denominator will approach 0, and we got those two here, right? So this is a classic 0 over 0. So we'll let L'Hopital settle this. And then we have the numerator, which is sine t, over we have the denominator, which is 1 minus cosine t, 8. And since it's 0 over 0, and we have, that's how we got this. So that's gotta be same thing as derivative, which is cosine t, over the derivative of this, which is sine t, right? And then do you see this is cotangent, this is infinity, right? This is, wait, this is not infinity. What am I saying? Why are we, I screwed up. We have to let this thing approach 2 pi, right? Let's do it at 0. 0 is the vertical. Oh my God. This is not infinity. This is of course 0. Let's make it approach 0. And then this is 1 over 0. You know what I'm saying? So that's infinity. So this is vertical. Therefore vertical. So what we have to do is we have to amend this thing. We have to go back and take every even number out. You know what I'm saying? So we have to go back and say, let's make a correction. That was not right. So we have to say t is equal to, let's say 2n minus 2n plus 1 pi. You know what I'm saying? In order to make it just the odd numbers. Because at even number, this is vertical. So far with me? Questions? Okay. What about second derivative? How do we take a second derivative of this thing? And some of you actually never figured this out last year, right? Okay, so let's do second derivative. Here's the theory behind second derivative. We want to figure out what this is, right? And let me remind you that thingy is that, right? Okay, remember dy over dx, what it looks like. That thing looks like this. Dy over dx looks like this. You know what I'm saying? So that's a function of t. So we will let z, which is a function of t, to be dy over dx, which is a function of t. Then this thing becomes this. You know what I'm saying? Which of course is same thing as this. Which of course is same thing as this. That's what that second derivative looks like. And this is not acceleration. Right? You know what acceleration vector looks like. This just tells you the concavity. This is one of the most useless thing in calculus in real life. But for some reason, mathematicians love this, right? Okay. So let's find it. Remember dy and dx. Let's do x first. Dx over dt. Dx over dt looked like this. R 1 minus cosine t, right? From above. And then dy over dt looks like this. R, what was it? Sine t, right? It looks like this. Actually, we don't need this thing. I'm gonna get rid of it. What we want is dy over dx, right? Which I'm calling it z. I'm gonna move this over. So this is z. Actually, I'm gonna move it here. dy over dx looks like this. Sine t over 1 minus cosine. Am I doing it the other way? I think I'm right? This was what it was. Maybe I should have write it in the first place. dt is equal to r and sine t. And then dy over dx is this thingy over this thingy, right? Now we're calling this c. That means we can find dz over dx, dz over dt. And quotient rule, right? It's solvable, right? U prime cosine t minus u sine t, or u prime cosine t times v, like that, and minus u sine t and v prime derivative. Is that sine square t? Okay, so far so good. Is it too much algebra if I just simplify this to be negative? So this is just cosine t over 1 minus cosine t quantity square, and then minus 1, eh? Too much algebra? Nay? Yes? Maybe? Anybody have a question about that algebra? I'm gonna move it here. And that thingy, of course, simplifies to this. Right? Don't need a parenthesis there. Yes. If it's too much algebra, now is the time. Okay, therefore, with this, which is same thing as dz over dx, right? dz over dt over dx over dt. So we take this whole thingy over this whole thingy. You know what I'm saying? So do you see this is negative 1 over r and 1 minus cosine t quantity squared? Do you see that or not? Okay, wait, did I lose r somewhere? Or did I screw up in Dropbox notes? Because that R is not there in Dropbox note, but it should be there, right? Do you see that R should be there? Maybe I should change the Dropbox notes. God, after all these years, nobody ever pointed that out, huh? Okay. What does that tell you? See, this thingy is negative always, right? Unless it's vertical and doesn't exist, which means this is concave down everywhere. You know what I'm saying? So it tells you this curve is concave down. And then if you look at the shape of this thingy, yeah, that makes sense. It's concave down everywhere now, isn't it? Other than the vertical stuff. Okay, so that makes perfect sense. Okay, then how are we doing in time? We'll just take a integral of this thing and we'll do arc length tomorrow, okay? This thing up. Now we want to integrate this thingy, meaning we want to find the area underneath that thing, right? So as always, we'll do rectangle approximation idea. So suppose we take that one rectangle. Then remember this is y and that is dx, isn't it? So we have my dA. dA has been always y times dx, eh? Say yes. Okay. What was y? Y was r, and then 1 minus cosine t, wasn't it? Then what's dx? R, 1 minus cosine t, wasn't it? What? Up here, see, that's dx. They are the same thing? Yes, they are. So what that gives us, of course, is r and 1 minus cosine t squared dt. Before we shove it into the
R squared?
Huh? Or r squared.
Squared?
Yeah. Good catch. Before we shove it into the integral, because we don't know how to integrate that thing, so we might want to square this thing out here. Like that, eh? Now, do you remember what to do about that thingy? What do we do? Well, you forgot everything, huh? Was it minus or is it plus?
Isn't it plus?
This thingy, this is plus, right? So it simplifies to 3 over 2 minus 2 cosine t plus 1/2 of cosine 2ta. Like that. Okay, now we can integrate. We'll integrate with blue. So my a is from 0 to 2 pi, let's say our area under one arch. And then we shove that thingy in r square and 3 over 2. That 3 looks weird. 3 over 2 minus 2 cosine t plus 1/2 cosine 2t. You want me to tell you how to do this in your head? Yeah, the answer is 3 pi r square. You get it? Well, that doesn't help now, does it, right? Think about this. What's the antiderivative of cosine? Negative sign, right? So this will be positive sign. But 0 and 2 pi, whenever you evaluate the integral from 0 to 2 pi, these are coterminal angles. You know what I'm saying? Once you plug in 0, once you plug in 2 pi, they give you exactly the same thing, so they cancel. I mean, sine gives you 0 anyway, but you don't even care, right? Actually, I'll evaluate it and explain. So this thingy becomes r squared here, 3 over 2 t, and minus 2, oh yeah, not negative, positive, sine t, or negative in this case. And then this thingy becomes sine 2t here, therefore we put 1/4, correct? And then let's try to evaluate this. R square and then t. If you plug in pi, right, that becomes 3 pi over 2.
I think it should be 2 pi.
2 pi. If you plug in 2 pi, then that just becomes 3 pi. You know what I'm saying? And then let's think about it. Sine 2 pi and sine 0 is the same thing. And sine 4 pi and sine 0 also is the same thing. These sine and cosine are periodic functions. So whenever, before that, from now on, this is very, very useful. Whenever you see sine, if you have a like t over 2, that's a different matter. But if you have just sine and cosine t or 2t, and then your limits of integration is from 0 to 2 pi, they always die. They give you exactly the same thing when you subtract. So we don't have to care. These things are 0. This is the only thing that's going to contribute. You know what I'm saying? So what you have is 3 pi r squared. How about that? So you can just take that shortcut. If you do that on the test, it's fine. I mean, you really don't. If you got this much, I'm going to assume that you know what to do from there. And then what we have is x is equal to hyperbolic cosine t. And by definition, this is known as e to the t plus e to the negative t over 2. And then y is known as hyperbolic sine, and which is by definition this. Now, and regrettably, and then I did not come up with this pronunciation. A lot of mathematicians pronounce this as kosh, which makes sense. But then this one is cinch. Cinch. Why is that cinch? I don't know, but that's what my professor said, so whatever, right? Okay, we need to combine these things, right? Okay. First thing first, so why don't we square both sides and see what that is, right? So if I square it, the denominator becomes 4, so I would have e to the 2t plus 2 times this thingy times that thingy. That is 1 now, isn't it? And then plus e to the negative 2t. And then y squared is e to the 2t. And then we have minus 2 and plus e to the negative 2t over 4. So far, so good. And then how do we eliminate t? Well, we can vertically subtract. So on the left-hand side, I will have x squared minus y squared. And right-hand side, do you see all the e to the stuff cancels out? And it gives you 1? Wow, that's nice. It's hyperbola now, isn't it? Now, when you thought, okay, that's a nice hyperbola, question, of course, is what happened to the other side, that thingy, like where did that go? Okay, let's just think about it. See, this is why the parametric is more powerful than just regular xy. Let's just think about it from the definition, this thingy. Can this be negative? And answer is no, because exponential function is always positive now, isn't it? So x coordinate cannot have this, doesn't exist. Your y, this thing can be negative, right? Depending on which is bigger. If this is bigger, then it could be negative. You know what I'm saying? So there is our thing. This is always positive for all t. So the other side should not exist. But then if you're looking at this thingy, oh yeah, that thingy exists, right? So how do we square the two? There has to be a way to explain where did we pick up this side that doesn't even exist. Remember extraneous roots thingy? That happens whenever we square both sides, and we square both sides here, right? Whenever you square both sides, something like that might happen. Do you even know why extraneous? Did I explain last year why that happens? Here's an example. X is equal to 1. Very nice, simple equation. What's the solution? X is equal to 1. Now I'm going to square both sides. And what's the solution to this? See, we pick up something that was not there. Whenever you square both sides, this is dangerous, right? 50% of the time, you might pick up something that ain't there before. That's known as extraneous roots. And not only it happens in this case, but it happens with the graphs and everything, right? So you have to know better. And then direction of the trace. Do you all see that it moves that way, in that direction? As t increases? Yeah. Okay, so that's number 17. Instead of cycloid, this thing is known as trochoid. And then can you see this arm rotating so that it's going to trace? Oh, that didn't. So that just disappeared on me, right? Okay, that didn't work. Like that? Okay, so that's being rotated around like this. Now, nevertheless, we can still figure out the coordinate of this thingy. So this thing is x right here. And that thing is y right there, right? So we need to find some kind of expression of x and y. And then, of course, this distance right here is d now instead of r. And this is still r right here. You know what I'm saying? And this is our angle. Do you want to call it theta or t? Oh, they call it theta, so we'll call it theta. Now, let's cut this thing right here and create that triangle. Okay. Okay, now, how long is this thingy right here? I need to exit the Dropbox and come back in because this is acting up. And it takes its time whenever there's an error. Okay, go back. You notice that my arm disappeared? I read that thingy right there, right? On the center. Okay. So how long is this thingy? Is it same as before? Is it still r theta? Which is the same distance as that arc length. I know it's kind of too far, but it rolled. You know what I'm saying? And then we need to know how much this is, right? That's same thing as this distance, by the way, right? Which I don't want to draw it there, but let's write it and draw it. How much is that? Is that d sine theta? Do you see it? Right triangle. And it's the opposite side, isn't it? And I'm going to erase it because that's confusing. So far with me. So now we have x. X has to be r theta minus d sine theta. You know what I'm saying? And that's exactly what we want now, isn't it? How about that, huh? Okay, let's figure out y. Y is that much, right? So your y here is this much minus that little thingy, right? So that little thingy, that side right here. Oh, not that side. No. I'm gonna have to draw this. I'm gonna have to draw this triangle back in. I'll do it with a different color, right? So this, I'll still write this thing in. This is d sine theta right here. And that side right there, do you see that is d cosine theta? Oh, I think we have it now, right? So y has to be this whole thingy minus that much is what y is, right? This is y. So that is r minus d cosine theta. And I believe that's exactly what we want, eh? How about that? Any other question or question about this problem?
Yeah, can you explain again how we know that the longest horizontal length is the arc?
Okay, remember this thing rolls, right? Without slippage, so that arc is the same thing as this amount of roll.
Oh, okay.
Right, and then arc length formula is r theta.